Okay, so basically the first step that you do is to use Coulomb's law. And we learned about that last week, and we also learned about it in the book, and it's laid out right here as F of the dipole on Q is equal to K Q1 Q2 over R squared. So that is your starting point in this problem. The next step is to calculate the differential forces, to lay out the differential forces felt by the test charge Q right here by the different ends of the dipole. So we have Q, which is a positive, and negative Q, which is a negative. And because the distance between Q, the test charge, and positive Q is longer than the distance between Q and the negative charge Q, there are different forces. So these are laid out right here and right here. And F net, which is what we're trying to find, is the combination of these two forces. So we can actually represent F net as KQQ, which is K, the constant Q and Q, minus over R plus 1/2 S, which is 1/2 of this distance here, squared, minus KQQ over R plus 1/2 S squared. So the difference is that one of these is negative and one of them is positive. And then you can basically just do algebraic simplification from here. You can pull out the denominator and make it a constant in front to simplify the fractions. Then use cross multiplication basically to find a common denominator. And this is just algebraic simplification. You can expand this section to simplify, and eventually it gets a little bit messy, but what you end up with is F net equals KQQ multiplied by 2RS minus S over R squared. So S, remember, is the distance from the ends to one end of the other end of the dipole, and R is the radius, or the distance between the dipole itself and the test charge Q. So, as stated in the challenge problem, S is much, much smaller than R. So basically, when S becomes much, much, much smaller than R, a fraction like S over R right here is looking like some value 0 over some value that's not 0. When you have something that's really small over something that's really big, it looks like 0. So it would be 0 squared, and then this would just cancel. It would be 1 in parentheses minus 0 squared, which is just 1. So this actually simplifies. This value gets completely gone, and then eventually you can simplify it down to KQQ minus 2RS over R to the 4th. Then you cancel the R's and you're left with this end here, which is what was represented in the problem.